Okay, everybody, today we'll be learning about the binary tree. It's the last data structure that we'll be covering, but it's by far the most important one. Okay, a binary tree looks similar to this structure. Now, what is a binary tree? It's basically a collection of nodes. Now, we already looked at the linked list with a collection of nodes, and it attached to each other from just one end. There was a head, and they just kept attaching to the head. Well, the collection of nodes are organized into a tree, and it starts from a root, just like a tree has a root. When we add a node, we have a root, and then we add leaves to our nodes. And basically, let's say we had to add this 3 next. Well, how do we add it? Well, it depends on if 3 is less than 7 or greater than 7. So because 3 is less than 7, it goes to the left side. Now when we add another leaf, let's look at our 5. Well, 5 is greater than 7, so it goes down our left. But 5 is greater than 3, so it goes down our right side of our leaf. Okay, so let's look at our 10. Well, 10 is greater than 7, so it goes there. And I'm going to change the formatting just so that we have more space, because now my left is going to point to this 5, and we don't want that to happen. So let's break it up a little bit more. Next, we're going to add the 1. 1 gets added to 7. 1 is less than 7. It goes down to our left. 1 is less than 3. It goes down to our right. Let's try and add another node. So let's say let's pretend we had a list of numbers. Instead, we're going to organize them into a tree. But how does that get done? 9 gets added to 7. 9 is greater than 7, so it goes to the right. Now we compare 9 to this right side. And 9 is less than 10, so it goes to the left. Let's try 8 now. 8 is greater than 7, so it goes to the right. 8 is less than 10, so it goes to the left. 8 is less than 9, so it goes to the right again. And finally 2. Where will the 2 go? Well, 2 is less than 7. Let's take it down that way. 2 is less than 3. Take it down that way. 2 is greater than 1. That's where our 2 ends up. And basically, how do we add these? How does this work programmatically? How do we build it? And it starts with a node. So we have to build a class node. We have a value, and we have a left and a right side. Now, when we build a node, now this is just a definition. When we build a node, it has to get sent a value. And then left and right, left is equal to null, and right is equal to null. So every time you create a node, by default, this will have a value, and this will be null, and this will be null. But how do we add? Now this is our class for a binary tree. And we start with root, a node root, just a definition. That's basically it. But how do we add a value to a root? Do we just say root equals new node 6? Now, if that was just the case, then we could build a bunch of roots. But we have to be able to do it recursively. So how do we add a new node to the leaf? How do we know if it's a node? Well, recursion offers an answer. Now remember, recursion has a base case. Base case will be our root. And then if we don't have a base case, we have 2 other cases, left and right. Let's cover that. So I'll show you. We can create something called private node, add recursive, current node current, and value. So whenever we call add recursive, we set it equal to node current in dot value. So if current is null, return new current value. So if I call this function, if I call this method, I say root equals add recursive, and I send it root, and I send it 6. Now we already have node root. We already created it. Now we're going to send it. We haven't constructed it yet. But as you can see, we have a constructor here. Let's just trace it. So add recursive. This is our root. We already created it here, or created the space for it. We send root, and we send our value, which is 6. Now, if current equals null, it is null, right? There's nothing here. So then we have that line, new node value, new node. Remember when we created it? New node value. So it gets returned here. Our value is 6, and this is our base case. So basically, this just creates a node and returns it to whatever called it, and it gets sent to root. So now root is equal to, what gets returned? Node root equals new node value, which is 6. So now we have a 6 here. So adding another node to our tree. This is the line we use to add another node to our tree, but this time we want to add 4. So eventually we want to add this node to it. So do we want to add it here or here? To the left or right? Well, because 4 is less than 6, we want it to be added here. So how do we do that? Well, turns out this is our line of code. If value is less than current value, because when we send this root now, root is going to be, well, let's trace it. So I have this code, and I send this root. That's root. It gets sent in as current. 4 gets sent in as a value, just like last time, but this time it's more important here. So what do we do? The value is 4. Is current equal to null? No, it's not. This is current. It's 6. So current is not null. That's the current. Is value less than current dot value? Well, that's current. That's current dot value 6. Value is 4. It is less than that. That's true. So now we talk about current dot left. Current dot left, that's that. And we call our function again, except this time we send current dot left into current. So now we have a new stack. Our new current is the left side, and our value is still 4. So our new current is null. That's true. So we're going to return new node and new node 4. So now we have our node, and there's a 4 in it. And we're going to return that to whatever called it, our current dot left. And that just gets stored right there. Okay, so what happens next if we want to add recursive 5? Let's say we wanted to add 5. That's our node. We want to add it somewhere. Does it go there? Does it go there? Or does it go there? Well, let's trace it. Lower numbers on the left, so 5 is less than 6. Lower numbers on the left, well, this is higher, so it has to go on the right. But we didn't define a current dot right, so we have to define that. And that's right here. So if value is less than current dot value, what if value is greater than current dot value? We have to define that. So let's run through our code and see how that works. We just said root equals add recursive. We send root again, and we send the number 5. So root gets sent in as our current node, but our value is still 5, right? It gets sent in from this function. It's not null because it's 6. Current is not null, so we skip to the next. If value is less than current dot value, well, that's current, and our value is 5. That's true. It is equal. It is less than 6. So now we say current.left. That's our new left again. That's our left, it's 6. But our value is still 5. We didn't change our value. Our value sent in. That's current.value. That's still value. We never play around with value in this function, in this method. So we send current.left as our new current. That's our new current. And we send in a value 5. 5 is just transferring unchanged all the time. Now, our new current is 4. Oh, ignore this. It's not null. Our new current is 4, is our node 4. Our value is 5. That's not null. Value is less than, that's value. Is it less than node current.value? No, it's not less than 4. It's false. Now we look at this. Is this value 5 greater than current.value? Yes, it is. So now we talk about current.write. Remember, this is the current. Current.write is null. So we send that out and we send a value which is 5, unchanged again. And now current is null. So we create a new node, that's the 5. And current left is the return node. Oh, sorry, it's current right. Whoops, I copied and pasted these. I'll fix it. Just ignore this, it's current.write. So it gets sent in. Our new node, which is this 5 node, gets sent in to current.write, and it just simply gets added to the right side of our tree. Now, your exercise for the week, and I'll give you the answers next week, is to try and create a situation where you try and delete a node. I'll give you the answers next week, but that's your exercise. That's your challenge for this week.